So again, if you want to look at the slides on your laptop while I'm giving the talk, they are here. It's part 2. So let me start by a short introduction. Yesterday we had a long introduction, so today a short introduction, which is basically for the few of you who could not be there yesterday, a summary of what we've seen. So first we are interested in what's called p-finite sequences, which are solutions of linear recurrences with polynomial coefficients. And to such a sequence, we associate a sequence of vectors. If the recurrence is of order d, we take the vector un up to un plus d minus 1. So you have d elements, d coordinates in your vector. And then the recurrence becomes a first order recurrence with a matrix an. That's the companion matrix of the recurrence. And then you can enroll the recurrence. So it's un plus 1 is an, un is this matrix factorial an up to a0 times u0, the vector of initial conditions. And we will focus on cases where a of n has a limit, finite limit. That's called a, and we call its eigenvalues lambda 1, lambda nu for those of largest modulus, and the other ones are smaller. And what we saw yesterday is that this limit matrix contracts a cone if and only if there's only one dominant eigenvalue and it's a real positive number. And that captures the asymptotic behavior of the sequence. This I haven't proved yet, but intuitively. And to prove positivity, we will construct a cone around the limit vector. Okay? And the cone, a cone, there are many cones contracted by A when it satisfies this, but we've seen a construction by van der Graaf using the Jordan form of the matrix. And with these cones and these properties in mind, you get a simple algorithm to prove positivity when there is a unique, dominant, simple positive eigenvalue. So the algorithm is this. First you check that the conditions apply. Then you construct a cone that has this property that it's contracted. And since the cone is contracted by A and an tends to A, for n large enough, the cone is also contracted by an. So you compute an m such that for n larger than m, the cone is contracted by an. And then you just have to check the initial conditions. So you start and you look at whether they're positive or not. If they're not, you're done. And then if you've gone beyond this index where the cone is contracted and you enter the cone, then you know that you will never leave it anymore. So you will stay in this cone. If the cone is positive, all the coordinates of the vectors are positive, then you've proved that your sequence is positive. So what this algorithm does is that it constructs a proof by induction of the positivity, and it proves the induction and the initial conditions. And we saw a special case, which is when the matrix is constant, which corresponds to a linear recurrence with constant coefficients, and that's the power method. In that case, we saw that the powers, now it's not the matrix factorial, an minus 1, and so on, since a is constant, it's just a to the n. The powers an, you divide by lambda 1 to the n to normalize, converges to a rank 1 matrix. And the vectors v and w are given as for you a right eigenvector for A and a left eigenvector for A. Okay, and then if your initial condition u0 is not in the hyperplane transpose of w u0 equals 0, then you will converge to V in direction. So it means in practice, you converge either to V or to minus V. Or you could, but the direction will be that of V. And it means you will enter the cone or enter the opposite of the cone and you will be rejected. So what makes the algorithm terminate, in general, so what I've shown now is when A is constant, the algorithm terminates if you're not in this hyperplane. So to make it work in general for a non-constant matrix, we need an analog of this power method. So that's really the basis of our work is this theorem by Friedland 20 years ago. And this theorem says that it works the same, almost the same. So you're given this sequence of matrices. It tends to a limit matrix that has the properties that we want, simple, dominant, real, positive eigenvalue. And then this matrix factorial, so you remember un plus 1 is this matrix factorial times u0. So we want to understand the behavior of this matrix factorial. This matrix factorial, normalized, again tends to a matrix of rank 1. V is the same as before. It's an eigenvalue, an eigenvector of A for the eigenvalue lambda 1. I don't say anything about W, right? And again, this means that if you take U0 outside of the hyperplane, transpose of W, U0 is 0, your vector in direction will converge to V. So at one point, it will enter the cone or its opposite. So you'll be able to either prove positivity or disprove it. So now your question is, what's this vector W? And I'm going to show you on an example that it's not simple. Can you read in the back? Okay, good. So I take this recurrence for the a priori numbers that were mentioned by Anastasia yesterday. So this is the recurrence. And I will show you the matrix so that you really see the matrix. So how do I construct the matrix? You take this recurrence and you want to construct the companion matrix. It turns out that in Maple there's a function to construct a companion matrix, but for a polynomial. So I just first turn the recurrence into a polynomial. Okay, now it's a polynomial, and I can get the companion matrix. It does it. I need to transpose it, and it wants the polynomial to be monic. So this is the matrix. Where I don't know where it displays. Ah, okay. Okay, so this is the matrix, and the limit matrix, maybe if you want to see it. Oh. So yesterday it was the screen. If I scroll, you see? If I make my window full screen, I think I'm dead because it's not the same window that I have on my screen on. But let me try. Who knows? But done. That's more difficult. I need to find my pointer. Here. Let me try. If it doesn't work, it doesn't care. Not very. Oh, and now I've lost this one. Okay. Good idea. Let me try this. There is this very natural command. Thank you. So this is the limit matrix, but we are not interested in the limit matrix. We're interested in the matrix factorial. So let's start with let's call M the value of say an when n is 0. Yes, no, that's my fault. Don't worry. So you see that 0, 1, and on the next row, you get two numbers. And then I will write the loop, where M is the result of evaluating an at n equals I times the previous M. And then I normalize, say, by dividing by the top left corner. Hoping that it's not 0, but that's why I started with this one and not the identity. So I have this matrix. I will try to show it. So you see, it's a simple matrix. You can. It's crazy. So let's look at the first row, and let's look at the second row. Okay, let's look at the first element of the second row and the second element of the second row. Okay, so, and you recognize the values. First, I can look at the, did I have the characteristic polynomial? No, I didn't have it. So let's take the characteristic polynomial of the matrix will be, you take the leading coefficient of this version with respect to n, right? The coefficient of n cubed. So that's the characteristic polynomial of that limit matrix. And you can look at its roots. It's a polynomial of degree 2, so you know how to solve it, right? And one of them is this 33.9, and that's basically what we had here. So that's the column. Now for the rows, what is this minus 116 something? I guess you haven't recognized it unless you know it in advance. It's just 1 over 6 over zeta of 3 minus 5, where zeta is Riemann's zeta function. Let's check it. Oh yes, it matches very well. Okay? So what this means, apart from the fact that Maple's interface is not so nice, is that for the vector v, we have complete control, and the coordinates are algebraic numbers, and life is nice. For the other one, we don't really know in general. In this example, what we know is that there's this proof by Aperi that zeta of 3 is not rational. So it means that if I take a vector of initial conditions with rational coordinates, it will be outside of the bad hyperplane. So generic rational initial conditions will be fine. But in general, we don't know anything. So that's life. Okay, that's for the summary. I also have an erratum. I showed this example yesterday, which was really copy-pasted. I cut and pasted the question from the monthly. And at the end of the talk, Pierre, who checks everything, told me, there's something wrong with this. I said, it's not possible. And also, I gave you a demo. I could show positivity. But actually, without knowing it, I cheated, because I didn't start from there, but I started from the solution that was published a few months later, where they corrected the question, and that's the question. So that's my erratum. And this one is the one that I demoed yesterday. So thank you, Pierre. So what do we have today? I will first really show you actual proofs of positivity, because so far this has been very theoretical. We've seen cones, but not real proofs. And when you try to do real proofs, you meet real difficulties. So we'll see what we can do, how we can try to be faster and really solve it in practice. Then I'll turn to sequences of cones that extends the method to areas that it did not capture at first. I will mention some of the things we can do for non-generic initial conditions, in some cases. And I will conclude with a proof of Frobenius theorem. So you see the numbers. The proof, it would be more natural to give it first, because then you have the proof, and then you turn to the application. But I will do as yesterday. I will run out of time, so I'd rather put the focus on the algorithms and go fast on the proof. But I want to show you the flavor of the proof, because what's behind this is really beautiful. Okay, so let's start with computations. So yesterday we started with this example of a recurrence of order 3. So this is the recurrence. The limit matrix, the limit of AN is this, and you can recognize that 5/16 is the coefficient of n in un divided by the coefficient of n in un plus 3. That's the 5/16, and then the minus 5/4 for the next one, and so on. So you have 3 distinct eigenvalues that are like in this picture, a dominant one and 2 conjugate. And because it's a companion matrix, the eigenvectors are just powers. The coordinates are given by powers of the eigenvalues, so it's really easy. In particular, so the first one, V1, has positive coordinates, clearly. So the cone we consider, that was van der Graaf's construction on an example. You take, you write it in the basis V1, V2, and the conjugate of V2. You put a real A, a complex B, its conjugate here, the conjugate here, and the constraint is that the modulus of B is smaller than A. So it's a real cone constructed from complex vectors. And it's easy to see that the matrix contracts, the limit matrix contracts the cone. Why? Because when you take a vector like this and you multiply by A, V1 is multiplied by lambda 1, V2 by lambda 2, V2 bar by lambda 2 bar, but the modulus of lambda 2 and lambda 2 bar is smaller than lambda 1. So you satisfy this even more. B is multiplied, B over A is multiplied by modulus of lambda 2 divided by lambda 1, which is smaller than 1. And then if I take mu sufficiently large, the cone is completely positive, and that's exactly this picture. Okay, so I have my contracted cone, and the next step of the algorithm is to find a point, an integer, where the sequence AN starts contracting the cone, not only the limit matrix, but the sequence itself. So how do you do this? You take, how do you check this? You take all the extremal vectors should be mapped inside the cone. So you take an extremal vector, and they're all parameterized like this. This, you take 1 for V1, C plus IS and C minus IS modulus 1. So those are the coordinates. You apply A of n, and then you go back in the basis of the eigenvectors. And then you look at the coordinates. So what you want is that first coordinate should be larger than the modulus of the second one. So an squared minus bn cn should be positive for all cs on the circle. And all n larger than m. And that's something you can, in principle, solve by, So this is, what is this an squared minus bn cn? It's a polynomial in Cs with coefficients that are rational functions in n, lambda 1, lambda 2, lambda 2 bar that are algebraic numbers. So it's a question that in principle should be computable by quantifier elimination. In practice, even for a relatively simple example such as this one, with the implementation I've tried, I had to kill it after 1 hour. Which does not mean that you should despair. So I will show you how you can do it in a different way using interval analysis. In this example, it's possible to do this. So let me do this. So this is the recurrence, the initial conditions. Again, I construct the matrix that now I don't know why you can see. The limit matrix, everything is nice. You look at the eigenvalues. Let's sort them by decreasing modulus. And if you look at the modulus, the largest one is 1.14 and the other ones are much smaller. And I introduce intervals. So the way I do this is that let me show you. I take these approximate values and I shake them. I put an interval of width 10 minus 10 around each of them. Of course, if you want to do this rigorously, you have to check that really there's a root in the interval, but that's not a difficulty. And I should say that these real boxes in Maple are actually Frederick Johansson's package ARB underneath. Maybe an old version of it. And for C and S on the circle, I just say it's an interval. They live in an interval centered at 0 and of radius 1. Okay, so let's do what was written on the slide. You take these vectors. Lambda 2, I need to distinguish the real and the imaginary part. So they're called alpha and beta here. You rescale the first vector so that it's bigger and you're sure that the cone is positive. So I multiply it by 3/2, and now you can see the other coordinates. And so we take a vector in the cone. It's a combination of those 3 columns by 1 for the first one and C plus IS, C minus IS. I can scale the first one and take 1, of course. Okay, and then you multiply it by AN and you come back in your basis. And this is what you have. You can normalize. And so this is the first coordinate, and you want to show that this one is positive. So the denominator is almost obviously positive, but it will be clearer with interval analysis. It's something like 1.8 times 16n plus 1, so it's positive. And its sign is 1. So we now focus on the numerator. Same thing. I take intervals. And then I want to explain what I'm doing here. I have this polynomial. Remember, I'm always interested in n positive. I have this polynomial. What I do is that I will lower bound all the coefficients. So I will take the smallest part of them. And then this one will have a leading coefficient that's positive. So it will be larger than Q of n0, where n0 is the largest root. Okay, so I look at the largest root, then it's positive. And so that will give me a bound on n, an upper bound on n. So let's take the lower bound on the coefficients. It's a polynomial of degree 1, so we can solve it. And we see that it's 0.4. So for n starting from 1, this is positive. So this was just for the first coordinate, but I need to check that the square of the modulus of the first coordinate minus the product of the other ones is positive. There's this small simplification that's actually using Robner basis inside, but let's forget about it. The denominator is clearly positive. The numerator, again, I rewrite it. It's getting bigger, right? So this is the one where I would want quantifier elimination to work, and with the implementation I had access to, I couldn't do it. But with interval arithmetics, again, you have a simple quadratic polynomial. You take a lower bound. The leading coefficient is positive. You solve it, and you see that for n at least 2, the cone is contracted. And then to conclude the proof, you have to check the initial conditions. You have to check that at one point you enter the cone. So let's do it. Let's look at the first 10 values. And I will take the vector L2 corresponds to, because the indices start at 0, so L2 is U1. So U1, U2, U3. So it may be a bit too early. Okay, anyway. So I will start a loop and wait for both conditions to be satisfied. And you compute the first vector, it's not the case. You compute the second vector, and that's the case. So what this means is that the first coordinate is positive, and a squared minus bc is positive, so you've entered the cone. And the proof is complete. So you've proved positivity in that case. Any questions so far? No. So that's good. But we had to rely on interval analysis. So that means that if we had had parameters in the recurrence, we couldn't do it. So for other similar recurrences, we have to find simpler ways that would simplify the problem before we can feed it to quantifier elimination or whatever. So one first simplification we can do is get rid of the algebraic numbers that were the eigenvalues. We will replace them by rational numbers. How do we do this? We just take not the exact cone, but an approximate cone. All of this is in an open set, so we have some freedom. So what do? We change the vectors. So this V1 tilde, V2 tilde are constructed from these approximations. 7/6, it's an approximation for the previous lambda 1, and this is an approximation for the lambda 2. Then you have to check that it works. It's really contracted in the limit. And this is the new cone. You see that it seems okay. And then the computation is simpler because you don't have any algebraic numbers anymore. So you do the same computation, and now you have polynomials in S and C as coefficients of here a quadratic polynomial. Life should be easier, and it is. So let me go quickly through the demo for that. So how did I take this 7/6? How did I find this 7/6 and the other one? You take just a continued fraction approximation. You take the first one, it's sufficient. Same for the other one. So these are the approximation. Why do I show you this? Because it could be that you take an approximation that's too crude and the cone is not contracted. Then you refine. Eventually, it will be contracted. Okay, so new vectors, new basis, new computation. We check that it's contracted, and it is. Everything is easy. Again, we need the cone to be. We need to find m such that n times the cone is sent inside the cone, as before, and we get something like 1 or something. 2. But that's just the bound. We see that for n larger than 2.09, the code is contracted, but that's by interval analysis. So I can check for n equals 2, maybe it already works. I know that for 3 and larger it will work. So I do it, and for 2 it works. And I can even check for 1, and it doesn't. But 2 is good. And then you check the initial conditions, and it's simpler than before because it has to be. Okay. And then we still have this c squared plus s squared equals 1 that we might want to get rid of. And we can. Because there's a further property that we can exploit in this example, which is that lambda 2 is inside this losange. So instead of taking the modulus of b to be smaller than a, we're going to take the real part plus the imaginary part in absolute value. And that will be sufficient. I have a smaller cone, but as you can see in this picture, it's here. It's still good. So you so now what do you have to check? You have only 4 extremal vectors, not an infinite number of them. And for each of them, you check the image. Everything is rational. I'm not going to show you the demo, but it's really clear. And you just have to check that linear polynomials are eventually positive, and that's something a 3-year-old could do. No. Well, anyway, that's something that's easy. So, of course, in this example, you don't need to do all these simplifications, but the example is not so difficult after all. So, but in general, this is crucial.
So, when you make a simplicial cone?
Because we don't know whether a simplicial cone will be contracted.
The number of braces that you mentioned.
Actually, yeah, exactly. We have more vertices than more rays than we would like. But maybe there are simplicial cones that are contracted in general, but I don't have a proof of that. Well, yeah, but then you need all the rays to be maybe. And then you also have to check the initial conditions. You get an index where you enter the code. Okay, so this losange thing is not an isolated phenomenon. It generalizes. I will not give you the details, but there's something called the Minkowski functional that for any subset of C, you associate a norm, which is basically relates where you are compared to the border of your polygon. And if you take a polygon with vertices at the roots of unity, then this norm has the nice property that it's submultiplicative. And so you can, what you do is that you constrain the coordinate. Each coordinate has its own norm, depending on the smallest Si, such that lambda I will be inside the polygon. In practice, we've never had to use it for S larger than 1, but I mean. Okay, and that works. This algorithm works. So there's an implementation by Alaa. And you remember there's this family of examples from the Gillis-Resnick-Zellberger former conjecture. And it's nice because the recurrence, the order of the recurrence increases linearly with k, but the degrees of the coefficients increases quadratically. So for instance here, for k equals 20, you have a recurrence of order 20, coefficients of degree 90, and the coefficients of these polynomial coefficients are integers of about 700 digits. And still, the proof, the automatic proof takes about 2 minutes. And this has not been optimized, and this has not been tried on a more recent computer. So it's good enough. And that's the picture in that case of where the eigenvalues are, which explains why it's not so difficult. So let's summarize. If we come back to the examples we saw yesterday, This is the one I showed today. This is the Straub-Zudilin sequence here. Gillis-Reznik-Zeilberger that we've just seen. There was this example from the monthly that was in the Eratom a few minutes ago. There was this recurrence in a paper by Miura and co-authors. And this nice theorem by Aharonov that I mentioned yesterday, but I will show it again. They can all be handled by this method. With a small subtlety. For those ones, it's okay because there's no parameter. But in those ones, there are parameters. So we don't claim that we can do everything with parameters. For any value of the parameters, we get a recurrence on which the algorithm applies. Yesterday, I showed you that for this one at least, we could do it even with the parameter, and we got a proof. For this one, we don't have it yet, and I will show you a special case of that one where to show you what we can do with parameters. So you take this function, and in the theorem by Aharonov, A1 is positive, larger than A2, which is positive. And mu1 is between 0 and 1. You expand this as a power series, and the theorem states that all these coefficients are positive under these conditions. You can ask Maple about the sign under these conditions, and it can do it. So what am I doing? I'm computing the sign of the coefficient, and I'm replacing the coefficient by its sign. So when you read t here, it means that the coefficient of t here was positive. If it had been negative, you would see -1. So it could prove positivity for the first 4, and for the last one, it just returns evaluated, which means it could not decide. Okay, the first 4 are positive, and we know the theorem is true, but we want a proof. So let me first get a recurrence for those. This is the recurrence. Again, I construct, maybe I should say that the characteristic polynomial has precisely for roots A1 and A2. So the eigenvalues are those numbers, and A1 is positive larger than A2. So we are in the conditions of the algorithm. So this is the part of the matrix AN, its limit. And this is my eigenvectors, 1A1, 1A2. Those are the eigenvectors. Okay, so again, I start, there's a subtlety. I start with Van der Graaf's cone, the one we've seen so far. So we take vector of coefficients, and we think C2 in absolute value is smaller than C1. So that's the cone. And we have to check that the same properties hold for the new coefficient. So these are the hypotheses. The first one is okay. So I have to maybe slow down on this. To prove that it's positive, I check that it cannot be negative. So I take this. Can it be negative with n at least 1 and the hypothesis here? And I give it a time limit. And it says no. So it proves that this is positive for all values of the parameter obeying these constraints. And it's very fast. Okay. Now the sum of coordinates also is positive, but then the difference of the coordinates is not. It is satisfiable. So I don't know. It's just that it is satisfiable with this constraint. So I'm saying, oh, but maybe n was not large enough. So let's increase n and try again. It is satisfiable. Third time. Okay, so then I ask it, but give me a value. So the function is satisfied. It tells me, oh yes, that's easy. You take n is 1001. This is A1, A2, and then you take those quantities. And you see what's going on here is that A1 gets very close to A2. That's a degenerate case. So we get that instead of looking for a fixed n, we can get an n that depends on 1 over A1 minus A2. And that is contracted. At this index, the cone is contracted. So I take n, and it's close to optimal because if I subtract 1 from here, then it tells me no, it's, I have counterexamples. So you have a family, so it's nice you have a family, a cone, but the contraction index, the time when it's contracted, gets larger and larger as A1 tends to A2. So you don't have a proof in that case. And also you need to check a number of initial conditions that depends on this difference, A1. Oh, mine. Intuition. Trial and error. Experiments. Okay, but there's hope. We don't have to stick to Van der Graaf's cone. We can try other cones. So let me show you a very simple cone that works. So this is actually the same as before, but now I change the conditions. The boundaries of the cone are that C1 should be positive, and C1 plus C2 should be positive as well. So it's in there. It's a cone, and it's positive. So I just have to check that it's contracted. So the hypotheses are these ones now. Same computation as before. I can get rid of the denominator n plus 2 because n plus 2 is positive, so it's not a problem. So now I have a polynomial. Can the first coordinate be negative? No. Can the sum of coordinates be negative? No. And then I just have to check initial conditions. And that's it. So the proof is complete in general with parameters. But there was this black magic of finding an appropriate cone. So the conclusion is contracted cones with no parameters were good. With parameters, it's still very much terra incognita. Okay. But as we saw yesterday, there are many examples of positive sequences coming from linear recurrences where the limit matrix does not contract a cone. And for that, I'm going to show you the result of Alaa that she presented at ISAC last year and at JNCF here. So maybe you can find the slides on the web with illustrations. So we had those examples where the limit matrix did not have a contracted cone, but it had an invariant cone. So the first one, top left, is the sequence by Waknin that behaves like 65 to the n times oscillations between 0 and 1, and nobody knows how to prove that it's positive, so I'm not going to prove it. There was this Turan's inequality on the Legendre polynomials that has 3 dominant eigenvalues. There was this nice or horrible, according to your tastes, example treated by Melzer and Mezarova, but also by Aline and Sergey, where you have a double dominant eigenvalue, so there's no contracted cone for the limit matrix. There was this other example by Aline, which is a bit nicer. And there's also this example of the same type. So this one is the one by Aline, and this one comes from this paper by Anderson, Vamanamurthy, and Vuorinen, telling you that this function, that's a hypergeometric function. I think we had examples yesterday of hypergeometric functions, maybe in your talk, Flora, well, maybe. We had allusions to hypergeometric functions yesterday. So, and the theorem is that you multiply it by 1 minus x to the 1/4, and it's strictly decreasing. But it's a function, so a priori, we're not dealing with functions here. So what happens is that the sequence of Taylor coefficients at 0, except for the first one, the constant one, which is 1, but we don't care, are all negative. So if and the radius of convergence is 1. So if you can show that they are all of the same sign, you have the result. And the picture is the same. One double singularity here. Okay, so that's for the limit matrix. But then what about what happens before infinity? Take a fixed n. What do you see? It's better. For those two, you have only two simple eigenvalues, and one dominates. So you have a contracted cone. For Turan's inequality, the same. The two complex ones here, actually they come from conjugate eigenvalues that at the limit tend to the unit circle. And then, unfortunately, this example is not so nice. The double root comes from two conjugate roots that collapse. But in all those cases where you have a contracted cone, there's hope, because we know how to construct cones. So the idea will be each AN has a contracted cone, or several of them. But of course, the cone contracted by AN is not contracted by AN plus 1. But the idea is to try and construct a sequence of cones, Kn, such that the image of Kn by AN is inside Kn plus 1. So if you enter there, you're done. So let me show this method on Aline's example. This is the recurrence, order 2. You don't have to read it, but they all look the same. Right? If you look at the eigenvalues, one of them behaves like 1 minus 2 over 3n plus blah, blah, and the other one minus 10 over 3n, much smaller. So it's this picture. And then you take truncations. So it's like what we did with truncated cones by taking rational approximations of the algebraic eigenvalues. We take rational approximations of these algebraic expansions. Okay? And then you put this constraint that I multiply it by 2 to make it positive, and this is the constraint. And then this is the picture. Because it's not a picture drawn to show the method, it's a picture from an example, you don't see as much as you would like. So this is the cone for n equals 3, I think, and I increase the radius so that we can see how they behave. At the beginning, they get larger on the left side, but you see the right side comes inside. So they are never included one in the other, but the image of one is included in the next one for n sufficiently large. And then these are the initial conditions. They seem to be always below, but at one point they enter the code. So those are the values, and I mean, checking this is really the same computations as we've done on all the examples. It's not difficult. It's easy to get this, and for this you have to go further. And for the other example, you take a cone that looks more like this. This 5 over 4, you have to take 5 over 4. You don't play with this. And for the other one, you could change. And again, it's easy to check that for n larger than 3. It works. So the method is really, you construct a sequence of cones in such a way that you can get a proof by induction. Let me show you the same idea in a more complex, or complex in the sense of complex plane at least, setting, which is Turan's inequality, where we have, so maybe you remember, maybe you don't, Turan's inequality, and some of you were not there because of various excuses. Turan's inequality was that Pn plus 1 of x, Pn minus 1 of x, minus Pn square of x is, has fixed sign. I'm not sure if I get it in the right direction. It's not important. And this is and Pn here are the Legendre polynomials. And this is the picture. Again, I have to fix a value. For the moment, we don't know how to do it for arbitrary x, for parameterized x. So I take x is 3/4. Then for, yes, x is 3/4. So then this is the recurrence for this sequence. So recurrence of order 3 for this sequence. Those are the eigenvalues, and you see that the second one, the complex ones, are at 1 minus 3 over n, which is smaller than 1 minus 1 over n. And then with this, we construct a sequence of cones, and they are contracted for n larger than 20. And again, you can check that it's entered soon. I have a demo for this, but I think now it's always the same thing, right? Okay. And that example was actually what we really wanted to get that to work, and that's what gave the idea to Alaa for the more general setting. And she got this sufficient condition, which is that for more general setting, now you have simple dominant eigenvalues in the limit, including the one. And you just have to control the speed with which the lambdas move and the spectral gap. In the example before, and in many examples, typically this will be of order 1 of 1 over n squared here, whereas this will be of order 1 over n, so that will be satisfied. And in that case, the method applies. Any questions so far? So I'm saying that the first part we dealt with contracted cones. The second part we deal with problems where we have an invariant cone in the limit that's not necessarily contracted, but it's contracted for finite n. And we can still deal with this. Yes? No, I don't know for a necessary condition. No.
So you have examples in which this is not satisfied, but still emerges the method?
I'm not sure. Alaa, do we have examples like this?
That this condition is not satisfied, but still the method because of the cones converges.
So the answer for everybody is yes. Okay. I just want to say a few words on this genericity problem. First, there are cases where you know that you are in a generic situation. And an example of that type is Aronoff's theorem. The general theorem is like this. You have k positive ci, you have k mu I that are positive whose sum is smaller than 1. And the theorem is that the sequence Dn is always positive. And what we know is that it's not difficult to see that the recurrence will have order k, and the eigenvalues are the ci's. We saw that on an example. But then we can do one thing which is, I don't even need to talk about singularity analysis. I think you can look at Adamar's rule. You have a Taylor series, then roughly speaking, dn grows like 1 over the radius of convergence to the n. And here the radius of convergence is given by the largest C1. So we know that we are in the generic setting, because the eigenvector is 1, C1, C1 squared, and so on. The other ones are smaller. So without any computation, but from outside knowledge, we know that the initial conditions are okay, so we get an automatic proof for any choice of the CIs. So it's always, we don't know from the recurrence and given initial conditions. We don't have any algorithm to decide if we have generic initial conditions. But sometimes there's exterior knowledge that can help. And it goes both ways. There's this, okay, I thought I had changed this, but that's not the problem. There's this nice paper by Dotsenko and co-author where they are in a non-generic situation, but still they can prove positivity. And the algorithm is general, so I'm going to try to show that, to show their algorithm. So first, they do some analysis, and they say that this power series has to have this radius of convergence. You can check numerically, it seems to be okay. But they prove it. Then it's easy to construct a recurrence for this. So for that, I think Anastasia mentioned that if you have an algebraic power series, it's definite. So you get a linear differential equation from the polynomial, and from there you get a recurrence. It has order 2. And then from the recurrence, you can look at the eigenvalues, and you get 2 eigenvalues, the inverse of the radius of convergence, but a larger one. So you know, because of the exterior analysis, that you are in a non-generic situation. So you are in the bad hyperplane. So what do? First, you pick random initial conditions, positive, and you construct a new sequence. It will behave generically, so it will be positive, and that you can prove automatically. So you have this new positive sequence Wn. Then, and that you can do with the algorithm. Then you construct, by closure property, a recurrence for this sequence, Wn plus 1 Vn minus Vn plus 1 Wn. Remember I showed you yesterday that you can construct recurrences. Okay. And because Wn basically grows like this to the n, this will be positive. And you can prove it automatically. So, using the algorithm, because now it's in the generic situation for the new larger recurrence. So you have proved that this is positive, and you have proved that Wn is positive. So if you divide, so you have that Un, which is Wn plus 1, Vn minus Vn plus 1, Wn is positive. And Wn is positive, so if I divide by Wn, Wn plus 1, what you have is that Vn over Wn is larger than Vn plus 1 over Wn plus 1. But what you know is that because this is generic and this is not, this tends to 0. So you have a decreasing sequence that tends to 0, so it has to be positive. And since Wn itself is positive, you have a proof that Vn is positive. You like it, right? And that's a general principle. If you have external information that tells you, I know it's not generic and seems positive, you can apply this. Yes? No, it's a random Wn will have the property that it grows like this to the n, so it's larger. So the question is, will it be a positive sequence?
No, but I mean the quotient could be like ultimately decreasing, maybe like not having this for any n.
But this one is ultimately positive. Wn is positive, and this sequence is ultimately positive because this grows like basically this to the n plus 1, and this is. Yes. Okay, and again, I am going to skip the demo. Yes?
This works for algebraic functions like this. What is the general setting of this?
The general setting is you have information about the non-genericity. The analysis part is not part of the method, right?
That's number 2, maybe.
No, I don't. Why? Why? Okay, we'll talk about this.
You should know that there is another one. The generic one goes faster.
But I have an example of order 6 where it works. I don't use or need order 2. I don't think so. So we'll discuss this. Okay. And then this is the end of the computational part. And I'm going to try to give you a flavor of where this theorem comes from. Why is this true? How do we get this property? And this was important for us. It was really the starting point for our method. Initially, we based our first algorithm on the proof of the theorem. And then we turned to other thing, and the Perron Frobenius theory for cones that I showed you yesterday. And the proof I'm going to give you is not Friedland's proof, because I think what we can get, what I will show you is more direct. And the reason we can make it more direct is that we have all those tools from yesterday. And I want to show you all the ingredients. When he writes an article, he just needs to give a proof. And he can use tons of results from the literature. I want to try to capture all the ingredients in half an hour, which I won't be able to do, but then you get a more direct proof.
Here, AN is any sequence of matrices or polynomial?
In his theorem, any sequence of matrices.
Any sequence.
Okay, and we had this. So the proof takes 8 slides. And if presented like this, it's horrible, so I'll try to break it into smaller steps. And first, I'll show you the ingredients. Then I'll show you how we get the proof with the ingredients. And then I'll try to show you some of the ingredients themselves. So first, with this hypothesis, we know from yesterday that there is a cone contracted by A. The hypothesis is there's a simple dominant real eigenvalue. And so there's an n0 such that for n larger than n0, an contracts that cone, because an tends to A. And then this is where it uses more background material that I haven't covered yet. There's a distance, pseudo-distance in K called Hilbert's pseudometric. And this is all work by Birkhoff in '57, very nice article. And it's a distance between directions, really a projective distance. So the distance is 0 when they have the same direction. The closer they get. Okay? And then when a matrix contracts a cone, the distance is really defined for each cone. You have a cone, you get a distance. When a matrix contracts a cone, then the image of the cone by the matrix has finite diameter for this distance. And same for the eigen. And then the really nice result is that all those matrices have a Lipschitz constant, which means that the distance between the images compared to the original distance is multiplied by a constant that's smaller than 1. And it's actually the hyperbolic tangent of delta divided by 4. No, but I think it's delta over 4 is in the parentheses. So hyperbolic tangent of delta over 4. And I put the graph of hyperbolic tangent in case you don't have it in mind. It's smaller than 1. So you contract directions. So so of course you start to see that there will be limit directions for the matrix and its transpose. And for the transpose, we need small extra ingredient, which is that transpose matrix contract the dual cone with the same diameter, but for the distance associated to the dual cone. And that's, in the end, you look at the definition and you write it and it's okay. Okay, so this is maybe mysterious. There are too many unknowns. So let me just show you Hilbert's pseudometric. There's a very nice book by Papadopoulos and Troyanov where you can find pictures. So let me do it step by step. So when you have a cone, you define an order on R to the D by saying that x is smaller than y for this cone when y minus x is in the cone. And now I introduce two quantities, capital M and small m. Let's start with maybe small m. You take x and y in the cone. There's a ray joining x and y, and it touches the borders of the cone at 2 points, this one and this one. So now we just have to look in the plane. And then you're going to look at x, and you want to x, you will add a multiple of y. So it's this dotted line is parallel to y, and you push this dotted line until it again encounters the border of the cone. That's the small m. And same on the other side, except that it's over m. So this is not very intuitive. And this notation is strange. Usually when you have a function of two variables, x and y, you have a comma. And here it's written x divided by y. The reason for this comes from the simple case where k is r plus to the d. So you have two vectors with positive coordinates, and you want to add to one as much as you can, but you have to stay positive. You think about it. The capital M is just the max of the ratios of the coordinates. And the small m stands for the mean. So that's the origin of this notation. But that extends to arbitrary codes. And then, with these things, this is the distance, the log of capital M over small m. Nice. So what can we see? I could prove it, but I don't know if you learn a lot. So this distance is positive. Why? Because capital M is larger than m. At least in this case, it's clear. The max is larger than the mean. dxy is equal to dyx. Let's do it in that case. The max of xi over yi is 1 over the mean of yi over xi. So with this, you get those things. Triangle inequality, it's the most mysterious, right? It comes from the fact that if you look at dxy plus dyz, and let me do it only in the real positive case, well, a product of max is larger than the max of the product. And then since you take log, that's the triangle inequality. Same for mean, but in the other direction. What else? This one. You take dxy, you can scale x or y and it doesn't change. That's geometry. If I increase x, so this line changes slope, and you know this, it's Thales. You look at your triangles and you look at your quantities. It's Thales maybe 2 times or 3 times. It's always the same, but it's true. And finally, dxy is 0 if and only if y is equal to lambda x. Well, you see, you have x, which is between an alpha y and a beta y. So for this to be 0, capital M should be equal to small m. So alpha should be equal to beta. The sup of alpha should be equal to the inf of beta. So x is y in direction. At least this gives the x equals y if we forget about the direction, but this gives the directions. So I said I wouldn't prove it, but I just gave an idea. Okay, so that's the distance we're dealing with. So now let's prove the existence of a limit vector. So I'm going to prove that the columns of Q, this product, AN, the matrix factorial, with V, the dominant eigenvector, the columns converge in direction to V. And that will come from the triangle inequality. So what do? First, since AN tends to A, the distance of ANV to V tends to 0. Because AN tends to A, AV is a constant times V, and the distance of constant times V to V is 0. So this sequence tends to 0. Now you define the one you're really interested in, which is yn is an, yn minus 1 with y0 is x in the cone. Then the distance of yn v, by definition of yn, it's the distance of an yn minus 1 v. And then I use a triangle inequality. I put an a and v in the middle. Now I told you an has a Lipschitz constant L smaller than 1. So the first term is smaller than L times the previous distance. And this is, by definition, the sequence epsilon n. And now you have a sequence of distances, so of a positive number, that satisfies un is L un minus 1 plus epsilon n with L smaller than 1 and epsilon n tending to 0. And that's sufficient to prove that the sequence tends to 0. That's first year exercise in analysis, maybe. What would you say? And thus, for any x in the cone, this sequence tends to 0. But what we saw is that this matrix has a proper cone that's contracted. In particular, a proper cone is solid, so it contains a basis. So you have a basis of elements, and for each element in the basis of RD, its direction tends to the direction V. So all the columns converge in direction to V. So that's the easy side. And the other side is the difficult one, the rows. And the rows that are those that converge to this mysterious W. And for that, we have to talk about duality. So if you've never seen that, it's maybe scary, I don't know. I've tried to put a picture, but they become ugly very quickly. So this is a cone, a simplicial cone, some would say, and it's dual cone. So anyone is the dual of the other. So and the definition is this: you take a subset of RD, and the dual S star is the set of Y such that YZ is positive for all Z in S. It's a scalar product. Did I say inner product or? It's inner product, okay. And the properties are this, and none of them is difficult to check. So I will maybe skip them. Just the last one is the one you're interested in. If A maps K to K, K is invariant by A, then the transpose of A has K star as an invariant code. And actually, also, if you had the, if A contracts K, then a transpose of A contracts K star. And it's really the fact that if you have transpose of A Y Z, it's the same thing as Y A Z. And then you just write the definition. Okay, so let's now do the other direction of the proof. It's more complicated because of the way you're looking at things. So you start with this transpose of Q, which is the, when you transpose, the products change order. I have to, I separate the first ones up to N0 because they don't contract the cone yet. So leave them aside. The part that's interesting is R, which is from N0 on. But the sequence we consider is not natural. You have UN plus 1 is transpose of R, and then you insert AN before Z. Before, we were just multiplying on the left. But now you take your product, you insert the new matrix. So it's more complicated, right? So we start with the UN0 inside the dual. And what will we do? So this is something that I've never used in my life before. We're going to prove that it's a Cauchy sequence. So you look at the distance of UN plus M to UN. So you just rewrite the definition. UN plus N plus M, sorry, it's transpose of R times the next ones, and Z is here. And UN, by definition, is transpose of R times Z. Now you see that you have transpose of R on the left. And it's the product of contracting things. And we know that the Lipschitz constant L dominates all of those. So it's bounded by L to the n minus n0, the number of matrices in the product R, times the distance between what's left. But we know that we have finite diameter. Because Z started in the dual cone, and when you multiply by those, you stay in the dual cone, because it's contracted by all those matrices. So this is bounded by a finite quantity, and L is smaller than 1, so this tends to 0. So this shows that the sequence is a Cauchy sequence. Okay, and then the Cauchy sequence has often, it converges. There are conditions for this. So you look up in your old math books, if you've never seen that since you were learning this. And here it's the case. There is a limit vector. That's for this part transpose of R, and then you multiply by the matrices that you had left out. And you get your vector W. So you don't know anything about it. You just know that it exists, that the theorem is proved. So I've left some of the ingredients to the end. I'm not going to give them because I want to jump to the conclusion, but just I will flash them. So the diameter, again, you use some Thales magic to see that there's another definition for the distance in terms of the cross ratio. But so there's a limit diameter. The transposition is easy, but again, you come to an alternate definition, a third or fourth definition of the distance as the sub for of those this ratio of inner products, and actually that gives you a method to compute the distance for polyhedral cones. And then it's again, oh, but if I have A here, I have transpose A here, and it will all work out. So the diameter of A for K is the same as the diameter of transpose of A for K star. And finally, Birkhoff's contraction ratio, and again, now the parentheses are correct. It's tangent hyperbolic of delta over 4. The proof, of course, I am not going to give it, but basically you start from U, it goes to AU that you can rescale to be in the same plane, and then you have to look at what happens when you move U here, you move here, but you have not only the derivative of A, but you have to take into account that the distances change. They are not the same on this ray and this ray, but it does the computation. It's a simple rational function of degree 1. You look at the derivative, find a 0, inject, and that's the formula. So it's nice, right? I mean, so let me conclude. The summary is that this algorithm is in the end quite simple, but it builds on a lot of material. This Perron Frobenius theory for cones, this Birkhoff Hilbert's pseudometric, and it handles many simple inequalities, contracted case, and we saw extensions when we only had an invariant cone, but for finite n there were contracted cones. Pointers for what we would like to do next, or maybe some of you would like to do next. This one is irritating. There's no reason why we cannot capture, we should be able to capture this. Why would the Melzaroba method by complex analysis do this and we could not? Well, clearly we cannot, but there's no intrinsic difficulty that should be an obstacle. It's just that we have to sit down and think more. The results of Alaa, generalizations of Turan's inequality, we should also extend this to other cases where the limit matrix has an invariant cone, but it's not necessarily just simple eigenvalues along the dominant circle, and find more classes of sufficient conditions where we can have a family of cones that proves positivity. And then the most interesting probably is understand what we can do with parameters. We've seen in some examples we have cones that behave uniformly with respect to the parameters, and we don't have an understanding yet of that. And I'm ready for questions.
So thank you. Are there questions, comments for Bruno?
Sergey as well.
Thank you for the very nice lecture. I have a very short and probably naive question. So in the a priori example, for the W, you had a Z of 3 for the W. But in the proof, somehow it was, for me at least, not clear at all that this will pop out. So what is the explanation for?
You mean how were we able to recognize Z of 3 in this example, or?
No, this you can do numerically, but
exactly.
I mean, what's the, how does the proof?
No, it's related to
that the set of 3 will occur, because this was just, it could be any constant in principle if you just follow the proof, but then it's really the one that is connected intrinsically to the sequence. So there should be a connection. This is what I'm saying.
There is. So a Paris construction, the purpose of it was that the sequence is not generic. So the connection constant, the choice of connection constant that you have to make to extend the radius of convergence is precisely this Z of 3. And that's why you see it for the non-generic, I mean, it has to come up somewhere.
question. Sorry. So, to make it clear for me, so you had to make a lot of choices in your algorithm. So you choose rational numbers, you choose this m somehow, or you compute it, but so how do you know? So, and then you certify. So that is how you do. But can you somehow compute beforehand the approximation or the magnitude of this m? I know that quantifier elimination is not good, but maybe you have at least bounds depending of the input sizes. Also for the approximation of the rational numbers you need. Understand?
Yes. So it's true that the way I presented things, it looks more like a method than like an algorithm. Because currently we don't have a clear understanding of what would be the best cone to make the method work. So what we have is that we have basic choices of cones that work. We take the Van der Graaf cones. It's clear that it's easy to see that it works. Then for the m, we haven't tried, but it could be that for this m, when the Van der Graaf cone is contracted, we could have bounds in terms of how the an tends to a, because we have it's a rational function, so we can compute the expansion. And for the initial conditions, it's more delicate because it's really, in a way, the distance to this forbidden hyperplane that we don't control. So we don't know how many steps we have to do before we are going to enter the cone. So probably there is a way to express that in terms of the distance to this forbidden hyperplane, and after that many steps related to this distance, we know that something will occur, but we don't have the proper definition of the distance, and we don't know the hyperplane anyway.
It might be related to a minimum singular value or something like that.
Well, it's true that the distance to the next eigenvalue plays a role everywhere. So yes, but not for the forbidden hyperplane. I don't think so.
So there are many more questions.
Yeah, thank you. So in the case where the matrices are constant, you said the W vector was an eigenvector of the limit matrix, and it's no longer the case in the final result. Is it related to the fact that they no longer commute, like the AI no longer commute, or is it something else?
Yes, yes. It's the case. We are not multiplying on the left any longer, we are multiplying on the right, and it's not the same. Yes. Okay.
Thanks a lot, Bruno, for this beautiful course. I think my question is related to your comment about this W hyperplane. Are you interested in computing it in some way, like computing intervals for the coefficients of this hyperplane?
Yeah, I didn't say that. That's right. But you saw in the example, I computed factorial 1000, sorry, and I already had many digits.
But would you be interested to having like an enclosure of it? Maybe if you have a proof that the coefficient contains some interesting value that you would like to approximate with a new method, maybe? No? With the Aperi numbers?
But I don't know how you... I don't know. If you can find an enclosure, possibly there's something interesting there, but I don't... Right now, I don't see how you could catch an enclosure.
Okay.
But in practice, the convergence is quite fast, and you can use acceleration techniques to get the values.
So I think it's time to stop and thank Bruno again for this wonderful talk.